Well, good evening, everyone. I am so excited to host again Precalculus Live. My name is Curtis Brown. Tonight we are talking about the AP exam year two, sort of a recap. Tonight I am joined once again by Vicky Carter, Tom Dick, and Steve Kokoska. I'm super excited to have them and host them this evening. I will not talk very much before we get over this, but just so if you're trying to follow along, we posted a link to the free response questions that you're going to be looking at tonight in the description for this YouTube video. And then we'll be talking about how we're going to work with the solutions and how we can link out to those as soon as they're posted. We'll put a link in there so you can jump over to the College Board website and check those out as soon as they're there. Not sure when they'll be there. The other thing is that we'll be doing these once a month, kind of like we've done in years past. And so the next one coming up, I don't have my notes in front of me, but we'll make sure to put a note in the chat. Please post questions in the chat all throughout the session. We'll be watching that chat, and I'll make sure to stop Steve, Vicky, and Tom if there's any questions that need to be answered directly if I don't know the answer. Otherwise, I'm going to stop my share and let Steve take it away.
All right. Thank you very much, Curtis. There we go. How's that looking? Can you see that screen? Working out
I
okay?
am watching. Yes, I can see that screen.
Beautiful. Well, thank you very much, Curtis, for arranging all of this once again. I am delighted to be back with you and Tom and Vicky and Erica in the background. It's great to be with you for another academic year. As in last year, we're going to start out by taking a look at the exam that was just given in May. And we're going to look at least at the two calculator or technology active questions as best we can here. If we have some time, we'll look at one of the other two free response questions. I'd kind of like to look at number 4 if we have the chance. So the way that I will do this is I'll look at the questions. I'll talk about a solution about how I might solve this and how I might solve it using technology. Specifically, I'm going to use the TI-Nspire, although Tom will come in and show you how to solve some of these with the 84. So I'll show you some of the technology, and I'll talk a little bit about how the points were distributed and a little bit about how these exams were scored. So again, I'm going to use the Inspire. Tom will probably do a little bit with the 84. I'd like to remind you once again that we do encourage lots of questions for those of you who are participating live. Please feel free to put any sort of question in the chat, and we'll do our best to answer that. We do encourage that. Curtis, Cheapers, I hope you're starting out the academic year well and you've done your homework and you're ready for questions.
Oh man. I'm still on summer break, Steve.
Oh no. I know we have lots of teachers who participate, but for the teachers who are listening, we do encourage your students to participate also. We think this is a good resource and a good opportunity for them. And they, of course, can ask questions also. And let's see what we can do with question number 1. Here we go. So this was the free response question number 1 on the exam in May. And it starts out with a tabular problem. And we have a function f that is decreasing. It's defined for all real numbers. And the table gives us some values for f at selected values of x. And kind of sneakily down here below the table. Whoops, why isn't that working? Whoops, I'm sorry. Let me try that again. Over here, there's an expression for this function g. And you notice it's got some coefficients in there that are decimals to 3 places. So boy, that's a tip-off that this is a technology active question. So in part A, we have a two-part question here. It says the function h is defined to be a composition. I call that or read that as G circle F. And this is a little bit different, I think, but I believe Vicky helped me, Tom. I think they did this last year. They actually give you the definition in the statement of the problem of the composition of G and F. I
Yes.
suspect that many of us on our exams in class would not do that and expect our students to know the definition of G circle F, that means G of F of X. But anyway, they're good enough to give us that in the statement of the problem. This says find the value of h of 1 as a decimal approximation. Or you know what? It might not be defined. And I underline this. I did a little bit of this ahead of time. In this problem, they're reminding the student to show the work that leads to your answer. But you know what? I'd like to encourage students, teachers, encourage your students to show the work that leads to any answer. You can't go wrong doing that. As we go through some of these problems tonight, I think we'll see this, where in some places points are awarded without any supporting work, but in some places you do need to have supporting work. So I think the rule of thumb should be, look, show the work that leads to your answer. I think that's important.
And Steve, this was added this year. It was not there on a similar question last year. So it is what you're
Yeah,
saying
remember
is,
that.
yeah, very
Yeah.
true that, we really want to encourage students to give us some lead in into how they're getting the answer that they've obtained and are reporting on the exam.
And it's tough too. I'm sure, Vicky, we get these questions all the time about, well, how much work do you need to
Yeah,
show? And you don't have to go overboard, but
no,
show the mathematics, right? That leads to your
yes.
answer. Show the math that leads to your answer. All right, in part A, I, if I've got that correct, we want H of 1 here. By definition, that is G of F of 1. How do I find F of 1? Well, I need to go to the table. So for an input value of 1, I get an output of 1.75. How do I get G of 1.75? Well, this is the technology part of this. I've really got to go to my technology here, my calculator, to get this answer. And I'll show you how I did this on the Inspire, and probably a little bit of overkill, but this is how I did it. On my TI-Nspire, I defined this function g of x, and there it is. And then I simply evaluated g at 1.75, and there's my answer, 0.333. Tom, Vicky may disagree with me on this one, but if I'm taking this exam using the technology, either the 84 or the Inspire, I like to set my calculator to fix 3. And here's why. I think that takes all of the guesswork out of reporting the correct final answer to 3 decimal places. If you set your calculator to more than 3 decimal places, like for 4, there's always a possibility, and we've talked about this in the past, that you could make an error in rounding. If you set it to 5 or 6 or even float whatever, that to me introduces another possibility of error because the student has to read that decimal and make a decision here about rounding, about truncating. So I set my calculator for fix 3.
So, Steve, I think this
Yes.
is an important conversation that teachers could have with their students, like right now, as they're
Yes.
beginning the course. Like, set your calculator up the way that you think is going to help you the most and use it that way throughout the course. So, in your case, you would want to go ahead and, check and make sure that I'm on that using the 3 decimal places every time I use it for any of my quizzes or tests or something like that.
Yep. Now we know that the calculator has stored these decimal numbers to the greatest degree of accuracy allowed by the machine. But this is what we're reporting for a final numerical answer. 3 digits rounded or truncated. The calculator rounds, and that's fine. That's accepted as an answer. Now, on the right-hand side of my screen, this is overkill for sure, but I just wanted to show you that you could do this, and Tom may have the opportunity to do this on the 84. I'm not sure. But you can indeed on the Inspire and on the 84 define a piecewise function. Now this is kind of funny here. We know that f, as they told us up above, is defined for all real numbers, but really I'm defining f by that table of values. So I can say that f of minus 2 is 14. So that comes from that table of values. Now the reason that I did this is because I just wanted to show you that the TI-Nspire does indeed do composition very easily. And so if I have my function f defined like this piecewise for those 5 values, and I have g defined over here on my other screen, g of f of 1, there it is, 0.333. That's kind of cool. All right, that's
So,
very
Steve, when I first saw your, we looked at this earlier to kind of
yes,
proofread it and everything. I thought, wow, that is so cool. I've
isn't it?
honestly never thought about doing that. My
Yeah.
only concern here is that if students use this technique, they might not have that work that leads to their answer because
Oh,
they may be
no question.
inclined.
Yeah.
Yeah, so it's something to be very careful about. If you think this is really cool, I'm going to try this. Just make sure that work is shown.
Yeah.
That's a
Yeah.
really
I
clever
wouldn't,
idea, Steve.
I like this. Now, I wouldn't recommend this on an exam for one thing because it takes too much time.
Time.
And Vicky, you're absolutely right. You need to show the work that leads to your answer here. And there might not be enough here showing that value of f of 1. You're absolutely
Right.
right. But it's kind of a cool thing that the calculator can do.
I mean, it shows us the power of the technology, which I think is so nice. And
Yep.
it may be something that could be very useful at some point in the
Yes,
course.
agreed. Agreed. In part II here, we need to find the value of, I'm going to read that as f inverse of 3.5. So what does that mean? We have to find a value that when we plug it into f, we get 3.5. We have to work backwards. So let's see here. I'm going to go up to my table, and I'm lucky enough to be able to find a 3.5 there. And I know that 3.5 came from an input value to f at 0. So I know that f inverse of 3.5 is 0. I wrote a little bit off to the side here, and I'm going to put an if and only if arrow here like this. Why is this true? Why is it that f inverse of 3.5 is 0? That is true because f of 0 is equal to 3.5. Now, I don't think there's really anything I could do here with technology on that one. I think this question was designed to just have us look at the table and get that
Yeah.
answer. And there you go. So that's how I would solve this one. Let's take a look at the model solution here. So one thing I wanted to say before I look on the left-hand column of this table is I've circled the points A1 and A2, and I think Vicky helped me, Tom. I believe in AP Pre-Calculus they did this last year. They have now done this for AP Calculus. Every single point is accounted for in
Yes.
scoring of the free response questions. Every single point. And so teachers now, Vicky, get a report and would know,
Yeah.
well, for example, all of my students got point A1, but they didn't do very well in A2. That's one reason for this, I believe. Another is for scoring, I think. And another is to make sure that we can map a lot of these questions to the CED. What
Yes.
what sort of essential knowledge statement are we testing, or what sort of objective are we testing? Anyway, the first point here was for the value 0.333. The second point was for this value here, 0. Now, I'll get into some scoring notes in 1 second. In the scoring guidelines, they have listed some general notes about, I think about these as sort of technology notes. Remember that final numerical answers are supposed to be given to 3 decimal places, 3 digits to the right of the decimal, rounded or truncated. And so we always get this question, well, wait a minute, what if the answer is 2.00? Do you need, or 2.300? Do you have to report the extra zeros in the end? And of course not. You don't have to do that. Sometimes students make a decimal presentation error. What does that mean? Well, maybe it's 3 digits, but they only report 2. So in this one, maybe they report something like 0.33. Well, they're not going to get that point. They're not going to get that first point A1. But that's considered a decimal presentation error, and students will not be penalized for any other subsequent decimal presentation errors in that problem. Okay. Let's take a look at the scoring guidelines here. There aren't many for Part A. It says up at the top here that that first point, A1, is earned for the correct decimal, 0.333, with supporting work. So what's the supporting work look like? Well, they made some suggestions here. F of 1 is equal to, you got to have that F of 1 somewhere, or a G of 1.75, or the 1.75 has to show up somewhere, somehow. A2 doesn't require any supporting work. Interesting. So if I'm reading that correctly, if I'm scoring this in part 2, if the student just writes down 0, well, they've got the answer, they've got the point. Okay, maybe not in my class, but in the scoring of this exam. In many of these free response questions in the scoring guidelines, there are these sort of tables for partial credit, and we're not going to go through those, but I just wanted to make you aware that in the scoring of these exams, we're trying to give credit to students for good pre-calculus work if they've demonstrated some good mathematics. And so those people on the development committee, those people scoring the exam have thought carefully about, well, if they've done this and or this, I think we believe it's worth 1 point. So there are these tables, and we're not going to go through them. We're not going to try to give you an example of how this works, but I wanted to make you aware that they do exist. Good. Tom, would you like to do any technology now, or you want me to go through problem 1 first? What's your preference?
Yeah, I might do a little bit, Steve. Also, I want to make a couple of comments about
Sure, shoot.
part A. So if it's okay, if you could back up a couple of pages. Let's see, one more page. Yeah, right to the original problem there.
Okay, shoot.
And the thing I wanted to point out was when I was first looking at this problem,
Yes.
when I got to part 2 of part A, okay, so right there at the very bottom, it said, okay, using the table values, F inverse at 3.5. Excuse me, the part 2 is find the value of F inverse at 3.5. And I remember myself thinking, well, am I expected to kind of make a leap of faith here that F inverse exists?
Very good question.
Because
Yep.
the function you define is going to work really nicely for values that are in that table.
Correct.
But this function F, as far as I know, these are just some selected values, and F could have other values. And I wondered, well, if the graph of F is doing some different stuff in between these X values, it may not have an inverse.
Correct.
But then I looked really closely at the stem of the problem,
Yep.
the very first part, and it told me that F is decreasing.
Mm-hmm.
And decreasing is meaning strictly decreasing. So it's not going to turn. I'll say it this way in loose terms. It's that graph's going downhill from left to right the whole way, and so it's not going to repeat any values doing that. And so we're really on safe ground there. But this gave me pause. It's one of those nuances, and I don't think it was. It was clearly from the scoring guidelines. It wasn't intended to trip students up or anything like that. Like, would they notice that nuance? They were just, you're told find this F inverse value, and they were really just looking that you're basically looking at a table and working backwards to the X value from the F of X value. So
yeah, and that you also know the notation. What does that notation mean?
Exactly.
I mean, so a lot of, to me, part A is not just can I do this? It's do I know what the notation is asking me to do?
Yeah, it's that function notation all the way around. Yeah, that's exactly. Yeah. So yeah, I could do just a little bit with the technology here.
Okay. Deal. Here you go. I'll stop my share.
Okay.
There you are.
And we'll see if I'm able to get this to work. So I'm using the actually online TI-84 CE, and we'll give this a shot. And
very cool.
As Steve said, yeah, you can do these. You could take that F of X table of values and actually define a function. I think what I'm going to do is I'm actually going to go to the stat editor and enter the table of values there, so I can at least maybe look at that graph of those points that X comma F of X values represent on the graph. So what I'm doing here is in that list L1, I'm just going to put in my X values. So L1 is going to be my X values, and they're just -2, -1, 0, 1, and 2. So we can enter those pretty quickly. And then in L2, I'll put the corresponding F of X values that were given, which were 14, 3.7, 3.5, 1.75, and 0.875. I think I got these right. There we go. Okay. And now I'm going to go to
Oh, did we lose him?
going to turn that on. And
We lost your audio there for a second, Tom. But
oh,
I think
okay.
you're good.
Is it better now? Okay.
Yeah.
It might be a unstable internet connection or something. Here we go. And we can see the X list, Y list. That's exactly what we want because my L1 was my X values, L2 was the Y values or the F of X values. And I'll go ahead and use the square mark here in color blue. And let's just enter and see what that looks like. And if I graph that, let's see. I think I got all the values but one of them. All right. There's, I think one of those values is off the screen, the one for -2.
Yeah.
So I could change my window a bit. Let's see. Or another way we could do it is I'm going to go to Zoom. And you see that number 9 down there at the bottom. Zoom stat will actually look at my values and figure out what would be a good window to show those off. There we go. And you can see it's all the Y values are positive. So it's giving most of my screen real estate is above the X axis there. And so we've got a nice look at those values. And then in the Y equals, in Y1, I'm just going to go ahead and put in my formula for the G function. So that was -0.167 X to the third. And then we've got plus X squared. And finally, the constant term is the minus 1.834. So that Y1 is serving the purpose of my G function. Steve showed on the Nspire, you can actually name the functions, F and G. Okay. Here on the 84, I'm going to need to remember which one. Well, I've got my F values in F of X values in a table or in those lists. I've got my G of X formula here in Y1. So if I go back to the calculation screen, if I wanted something like, let's see, we wanted G of F of, was it, what was that first one?
G of F of 1.
1, okay. So I could look up F of 1, which was, I think, 1.75. I could look at that, and so we can just pull up Y1 and put in the 1.75 right here, get that value. Or alternatively, we could actually graph, there's my G function, and I could actually trace, let's see, that's actually tracing my stat values from my F of X table. I hit the up arrow, down arrow, it goes to Y1, and we could just, on trace, I could put in 1.75, and again, see that 0.333, so. Yeah, so it's just a couple of things. To me, and Vicky, weigh in here. It seemed to be, given a table of values, this might be a natural way to approach it on the 84 is actually get those values in the stat editor. So especially given some of the later parts of this question.
Yeah, and also, it makes it kind of clear that you can see that decreasing nature of the function looking at the plotted points that you have there, which I think reinforces maybe something that we're going to see in a few minutes.
Yeah, I'm sure. Right.
All right. So I'll stop the share and turn it back over to you, Steve, unless
okay, deal. That's good.
Comments. Okay.
Curtis, while I'm doing this, any questions at all?
Nope, we haven't seen anything pop up in the
Okay.
chat.
All right, let's take a look at part B. I like this one. This says find all the values of x as a decimal approximation for which g of x is equal to 0, or there might not be any values. Let's handle that one first. So what I need to do is I need to solve this expression here where g of x is equal to 0. Well, there's no way that I'm going to do that by hand. I'm certainly not going to be able to factor that. This is clearly a technology active question. So this is the way that I did it on the Nspire, and Tom will show you some techniques to do this on the 84. There are a couple of ways to do this on the TI-Nspire. I like to use the command zeros here. So this is finding the zeros of g of x, finding the places where g of x is equal to 0. And the reason that I like to do this is because I can store the answers. It puts these answers in a list. Now, once again, these numerical values are displayed with 3 digits to the right of the decimal, but remember that they are stored to a much higher degree of accuracy. But one of the reasons I like to use this command on the TI-Nspire is because now, if I have to, for some reason, I can actually refer to individual values in this list. In other words, this is kind of like Z sub 1, this is Z sub 2, and Z sub 3. And I like that. I can pull these into a list and spreadsheet page. I can pull these into another computation or calculation if I need to. I really like that. Now, some of our students like to solve these problems visually on a graph screen. And so I did that on the right-hand side over here. Here is a graph of g of x in a reasonable window. And what I did is I used on the Nspire, I used the command to analyze this graph, and I was able to find the 3 different zeros, put those points on this graph screen with 3 digits to the right of the decimal. And I think you can see that those agree exactly with what I got on the left-hand side. Is one better than the other? I'm not sure. Certainly the one on the left-hand side is a little bit quicker. But it's nice to see this visually too, to get some sort of graphical confirmation. So the 3 answers that I need to report here are right there, all with 3 digits to the right of the decimal.
And Steve, I know the graph takes a little more time, but I like seeing is believing. Like, okay,
Yeah.
You told me I have 3, but I want to see them. And it's very clear from that graph that there are 3 zeros.
So being a pre-calculus course too, so one might ask, and not on the exam, but as a follow-up here, we might just think about, well, how do we know that there are only 3? Could there be another one off here beyond 6 to the right, beyond -2 to the left? So maybe we'll just leave that as an open question, Curtis, if anybody's out there. How do we know that there aren't any more? Okay. In part B, number 2, it says, oh, we need to look at end behavior of this polynomial function as g, what is it? Increases without bound, and then we want to express that behavior using the mathematical notation of a limit. I'm going to sneak down at the bottom here. Well, I know I probably overdid this too, but I'm thinking out loud here. As x increases or decreases without bound, we have a polynomial. And so the end behavior of this polynomial is determined by that term with the highest power of x. So that term is this minus 0.167 x cubed. So here's how I reason. As x decreases without bound, as x decreases without bound, what is x cubed doing? Well, that's getting larger and larger and larger negative. I'm multiplying by a negative number to minus 0.167. And so the whole thing here, oh, it's increasing with bound.
Yes, increasing.
Pardon me. As x increases without bound, this is increasing without bound, getting larger and larger positive. I'm multiplying by a negative number, which makes that very large negative. So that means that leading term, not coefficient, that leading term is dominating this polynomial and is decreasing without bound. How do we write that in limit notation? I would read this as the limit as x goes to infinity of g of x is equal to minus infinity. And this is very easy to do on the TI-Nspire. There is actually a template for a limit. So I can use that template and just plug in the variable and the value here. Well, not a value, but the symbol in this case, infinity. Find a limit as x goes to infinity of g of x. And in fact, the TI-Nspire returns that exact symbolic answer, minus infinity. And that's really cool.
And Steve, go back to the graph. Go back to the
Oh, I'm
graph. The
sorry.
graph has a power, though, of also giving them that visual. So to me, it's kind of a 2-for-1 when I do the graph and find the
Yes.
zeros. I've also got that visualization of what's happening without bound.
Yes. Agreed. Okay. Okay, so here's
I think you might need CAS though on your Inspire in order to do.
Yeah.
Kind of look.
all right.
Yeah,
So
you
here's
need the cast part for that.
Here's the model solution. Any answers yet to that, Curtis, about why we know there's only 3 roots there, 3 zeros?
Well, we got a statement here that talks about a cubic function will have a maximum or at most 3 real zeros.
Very good. Excellent.
Mm-hmm.
Excellent. All right. So there are 2 points here in part B. 1 point for those 3 values. Boy, there's a lot into that. And 1 point for describing the end behavior with limit notation. So we're looking for something like this, and they get 1 point. So here are the scoring notes for part B, and this is interesting. In the scoring notes here say, well, for that first point in part B, point B1, it doesn't require any supporting work. So the student could actually go, correct me if I'm wrong, directly to their calculator, go to a graph, find these 3 zeros, write down the 3 values, not even say x is equal, but just write down those 3 values, and that's the first point.
Yeah.
So they don't, in some sense, they don't need any sort of mathematical setup. They don't have to write down something like that. I think it would be nice if they did, and in my class, I'd like to see that, but they don't for the exam.
Yeah, Steve, scroll a little bit so we can see the scoring things.
There you go. Is that all right?
No,
Okay.
we're still on the calculator screen.
I'm still seeing the calculator screen stuff, or the your solutions there, Steve.
All right. Well, let's see. I don't know why that is true. I will try this again here. I'll try to share. Let's do this. See it now?
Yep.
Yes.
Yeah.
There we go. Okay. Okay, so the second point here requires a correct limit statement, of course, with 4 components. We're looking for the limit, LIM, x going to infinity. We want to see the function g, and we want to see minus infinity. Now, of course, in my class, and I presume in yours too, I really want to see a statement like this. Okay, but there are some other things that are allowed here, and the student will earn the point. I think this is in the context of, look, this is a high stakes exam. It's a timed exam, and we're trying to see what the student knows, can convey their knowledge of pre-calculus here. And so even if a student writes something like this, with nothing in between, they have these 4 elements. They have the LIM, they have x going to infinity. They have that function g. They haven't connected it with an equal sign, but there's the minus infinity. And so that's okay. I put a little asterisk down here at the bottom because this is kind of interesting. Sometimes students, when they're solving these problems, they like to go on and give us additional information, tell us a lot about this stuff that we didn't ask for, but they're going to tell us anyway. Sometimes we ignore that. But in the scoring of this here, it says if the response includes additional complete limit statements, the statement must be correct. So this is a little unfortunate, but if the student gives us the correct limit statement, the one that we're looking for, but then goes on to tell us something incorrect, they will not earn this point B2. So be careful, right?
So Steve, I don't know. I've been trying to think about this. Either students not understanding what it means increasing without bound or decreasing without bound, or teachers frequently on their personal test ask them for both
Ask them for
limits.
both, sure.
And
Yeah.
so students are kind of like, okay, well, my teacher always asks for both. I guess I better put both,
Mhm.
that kind of a thing. So,
Yeah. Yep. Okay. Very good. I'm not going to go over this page, but once again, there is a table here for partial credit. Tom, do you want to do some technology? Shall I look at C first?
Go ahead and look at C first.
Okay, let's take a look at C. Vicky, I'm going to need a little help here when I get to this table, okay?
okay.
How I was thinking about this one, and maybe you'll have a different way to explain it. So based on the table of values that are given here, which of the following function types do you think best models the function f? Could it be linear, quadratic, exponential, or logarithmic? And finally, give a reason for your answer in this first part. So, okay, so here's how I attack this one. In the AP Precalculus course, it seems to me that students are initially trained to look at successive differences over equal length input intervals. So I think that's the way that I attack this.
Yeah.
Now, my colleagues might say something differently, but if I have no idea what this function model should be, whether it's linear, quadratic, exponential, or logarithmic, I'm going to take a look at the successive differences over these equal length input values or intervals. So I did that in a list and spreadsheets page. Let's see. Here are the input values of f. Here are the output values of f in column A and B. In column C, I found the differences. So 7 minus 14 is minus 7 and so forth. And once I see that, then something dawns on me here. I can see easily or easier. I agree that might be able to see that from looking at the output, but I can see easier here that I can multiply by a half to get from that minus 7 to 3.5, to get from the minus 3.5 to the minus 1.75. And to double check that, I just took a look at some ratios.
Yeah.
So I took a look at 7 divided by 14, 3.5, and they're all the same over here. So what does that tell you? Because these ratios of these output values are all the same, it is most likely modeled by an exponential function, could be an exponential function.
So
Now,
no, go ahead. I just, when Tom was typing those values in with the
yes,
TI-84,
yes,
for me, it was like really clear as he
screaming out
was
at you.
saying, screaming
Yeah.
at us, not screaming, but it was 14, 7, 3.5. And I'm going, wow, even if I looked at the table and didn't see that, as I'm typing it, it became very clear.
Yeah.
It was just kind of eye-opening to me when Tom was typing those values in on the 84.
I think from my perspective, I am trained to think about finding the successive differences first.
Okay.
In the back of my mind, I'm reading this question and say, well, it could be linear, could be quadratic. And so I'm looking for the first successive differences being constant or the second successive differences being constant. And so that's why I did it this way. I agree completely, by looking at this in a table, well, oh boy, now I can see that the proportions here, those output values do change proportionally by this scalar, by this factor of 1/2, and therefore f could be exponential. So I noticed that using technology, or I noticed it in a table that I completed by hand. I wrote something here about that observation, and therefore f could be exponential. And I felt obliged to show you this on the TI-Nspire. Some teachers ask me, well, which calculator would you use if you're doing AP stats? And wow, the Nspire is absolutely wonderful. It creates this graph almost effortlessly. It's wonderful. And I can see now that those points sort of fall along this exponential curve. I feel very good about my conclusion. All right, so here's the model solution. In part I, worth 1 point. We're just looking for that answer. An exponential function best models it. In part 2, 1 point, we're looking for your reason, examining the ratios of those successive output values gives you the same ratio, gives you the same value, 0.5, and therefore it should be exponential, could be exponential. So there are some scoring points in here for part C. I won't go through everything with you here. Again, point C1 is earned for just coming up with that correct function model just by simply saying exponential with no other work. The reasoning is in part C.
Hey,
Go ahead.
Steve,
Yes.
I'm sorry, I missed this in the chat till just now. There was a question about successive ratios.
Yes.
So is there a function to do successive ratios as there is for successive differences? That's the question.
I don't believe there is on the Inspire. I think what I did is I set up my first cell as a ratio, and then I was able to fill down. Tom, I don't think there's a function built in for successive ratios on the 84, is there?
No, I don't think so. I think you could do it as a use the sequence command to do it,
Right.
and
Mhm.
then and that would work okay. But there's not one that's built in. You'd have to
Yeah.
You'd have
That's
to
a good
construct it
question, Curtis.
yourself.
Good question. Good technology question.
Yeah.
Yep. Thanks, Gerald.
I think this is important here. Certainly, I would guess that readers, graders saw this frequently, where students earned both of these points sort of at once by giving their answer and explanation in a sentence or two.
Mhm.
This third bulleted item over here is saying more about what is required to earn that second point. There must be references in some way to the output values and input values from the table, or successive output values are decreasing proportionally by a factor of 0.5. And I wanted to point out this one here, this fourth bulleted item. You know, some students will look at this and automatically think, well, I've got this fancy exponential regression command in my calculator. I'll try that and see what happens. And now I didn't do that, but I'm pretty sure that if you were to do that, the R squared value would be really high. And that would suggest that the exponential model is very good, is a good fit to the data. But that's not sufficient in this case. That's not what they're asking you to do. They're not asking you to find a model through exponential regression. They're asking you what's the best model in some other way by looking at these successive differences, by looking at these successive ratios. And there was a special case down here, which I'm not going to go through. That's kind of like this partial credit thing. Cool. Tom, that takes care of question one. You want to do a little bit more technology?
Sure, Steve. Yeah, I'll
Okay.
give it a shot.
There you are, sir.
Okay. All right. Let's see if I can pull that back up again. And look, are you all seeing the TI-84 there?
Yes.
Okay, great. Okay, so I'm going to actually go ahead and look at that graph of the function g. The part that Steve was finding the zeros. Just wanted to point out something on the 84. Let me go to the y equals. I'm going to turn off the stat plot for now.
Okay.
And just do a zoom decimal window. Let's see, number 4. And
Oh, cool.
it actually shows all the zeros. That turns out to be a fairly good window for it. And we can go to the calc menu. So that's the second shift of the trace, and calculate a 0. And left, I'm going to go over to that left one first, a little bit to the left of it, hit enter. Go a little bit to the right of it, hit enter. Now I could go in between, but I'm just going to go ahead and hit enter for my guess. And there's that first 0 that Steve found. Now, what I'm going to do is now I could go over and calculate another 0. So a student could either do the following. They could jot this down right now, this particular x value. But what I'm going to do is I'm just going to quit temporarily to the calculator screen and just hit the X key. And there's that 0 right there. So now it's been recorded on a calculator screen. Now I could store it, but I'm just going to leave it there. And now go back to the graph, hit calc again, hit 0, number 2, and go over to the next 0.
Tom, just checking while you're doing that, on the 84, if you're picking your left bound and right bound, can you physically type in a value for the left bound and the right bound?
Good point, Steve. So I'll actually do that on this. I'm fairly close here on the left. Let me hit enter. And I can see that 2 is a little bit to the right. So I'm just going to type in 2.
Okay.
There did. It gave that as my right bound. So I didn't have to. I think you were noting that I was having to hit the arrow key repeatedly to get over in that vicinity. It goes fairly fast, but yeah, you can eyeball a good value for the left and right. You can just type them in like this.
Okay, good.
Here I will arrow over a little bit to the middle, hit enter, and there's that second 0 that we wanted. And again, same strategy. I'm just going to quit to the calculator screen, hit the X key, and notice the X value is different now. It's the latest 0 that I found, and there I have it there.
Tom, before you leave that screen, this is probably
Sure.
a question for Curtis. I'm not sure you can do this, but if I wanted to, can I take that current value of X and store that in your stat list editor in that table?
Sure.
Okay.
Yeah, if you wanted to
Is
dump
there-
those into a spot, you can hit the store key and store that to a list editor spot just like you can anywhere else.
So if
Um,
you
If
type
I
in fact,
just
if
hit
you
in,
just hit X right now, you should be able to evaluate it right there. Like
Oh,
that's
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 cool.
probably the fastest way to do
That's
it.
really
Yeah.
cool. Okay.
yeah, and now it's kind of safely tucked away in this
Yeah.
here. Yeah.
Yeah.
It's displaying in this case 4 digits, but if you arrow up one,
Right.
you
If
can
I arrow
see
up onto it, then if we
got
look at
them
the
all.
bottom of the screen, we see actually a lot more
Yeah, that's
digits
really
to that.
cool.
Yeah. So yeah, that's a nice point. Also on the calculators, the home, I call it the home screen
Yes.
here. I could also store these values away in other letter variables. Like the first
Gotcha.
one I could store it in A, the second one B, the third
Yeah.
one C, and
Yeah.
then they're safely. I don't have to worry about what's happening here as I move the X on trace or whatever. As I move around, the X value is changing.
Yeah.
Mhm.
And so I've lost it unless I've either recorded it on the calculator. And here I'm thinking for this particular question, the student's going to need to report these. So they want it, where they can then
Yeah.
write these down accurately on their paper. Yeah. So I won't go, but you get the idea how you can find those values. We could do the third one in the same way.
Mhm.
Now, the other thing I was going to do is just go ahead and do maybe a quick regression on that data, see kind of really what it looked like. So
Yeah, let's do that.
go back to y equals, and I'm actually going to turn off y1 and turn on the plot.
Okay.
There's our data. Oh, that's right. We don't see the -1 and -2 values. So let's do a zoom stat. Quickly, there we go.
Oh, cool. Okay, good.
All right. And then let's see. I think we wanted to calculate a regression on this.
Yeah, let's try that, Tom. I like
Now,
it.
you point out, Steve, in the scoring guidelines, you just said, hey, I did an exponential regression, good fit. That's not going to cut it.
Right.
But what
Right.
I'm thinking, really, just even choosing exponential is kind of fueled by the observation, like what Vicky was saying, is just as those values were being typed in, it's like, oh, wow, it's half time down there. So that's kind of giving us some idea that this exponential would be a good fit.
Mhm.
Let's go to stat and go over to calculate. And we see we got 1, 2 variable stats, median. Oh, here we got all our regressions. So I'm going to just scroll down. I don't see an exponential regression. Oh, there it is. I had to go down there, exponential regression. Let's hit her there. X list, Y list. Oh, that's convenient. Looks good. And I'm going to actually want to store this away. And so what I'm going to do is store whatever regression equation it comes up with in Y2. So I'm going to pull up my Y variables. And then we'll just calculate. And first of all, it shows it to me in this kind of display format. It says, okay, this is a function of the form A times b to the x. And b is going to be that multiplicative factor. And notice, see that 0.5? That's it. Okay, it's not a coincidence that we saw things going down by a half. And the 3.5 is going to be the value that corresponds to x equals 0. Okay, so very good. Let's go back to y equals. And if you see, look at y2 there. It's got it actually put in. And it's funny, it's like, wow, a lot of digits on that something close to 3.5 times.
Really?
And let's just go ahead and graph y2. Wow, just goes right through those points really nicely. Okay. I would just add this quick comment that this really is just a model. You might say, hey, that's a perfect fit for those 5 points. Therefore, that is the formula for F. We don't know what it was doing in between. We know it is a decreasing function. So we got we know something about what the graph's doing in between these data points. But we don't know that this would be a perfect fit for all X values. It's a great fit for these 5 for sure. But okay. I'll jump off that soapbox and bring it back over.
Tom, before you leave
sure.
this, just for the heck of it, and we might need help from Curtis or Vicky on this. I think the 84, when it does a regression, stores the value of R squared somewhere. Can you get that? Is it in vars and stats? Is that where it is, Curtis?
So because this is a exponential, you did an exponential regression.
That's right.
Yes.
So the way the 84 works, it does do a transformation on that data.
Correct.
Fit a line to it, and then it retransforms the data and retransforms the line. So we do get a value of R squared, but that R squared is actually a measure of the percent of the variation explained by that linear model on the transformed data. So it's you have to be careful about what that R squared value actually means for this particular graph. But yes, you can get a hold of it if you need it. And VARS is certainly a way to get it. It should be calculated. Although, Tom, if you don't have the diagnostics turned on, I know it doesn't display them if you don't have them turned on, but I don't know that I've ever looked to see if it calculated them even with the diagnostics not turned on. I don't know that I've ever tried that. So
go to vars. Go
ahead and go to vars and go to stat vars, number 5 statistics, and you should be able to go to equation EQ. And go down there to R squared.
Okay. Great.
And there may be a value in there depending on what you've done in the past.
And see, this is why I believe students who did this, they looked at R squared and said, hey, you know what? This has got to be an exponential model. If you got something like an R squared 1 in the real world, you'd think people made up the data. That never happens in the real world. Never.
Well, yeah, that's 100% true. And again, like you said, we fit it to those points. We don't know much else about F, but we do know how the 84 does this thing and does that transformation. So that R squared is based upon the transformation of F.
Okay.
From an exponential function to a linear function.
And I think this is a really good discussion because I think there's a lot of teachers that don't know that. I mean, personally kind of became more wise about what was going on with R-square values once I taught AP statistics, because it was very enlightening there about, you know, you just can't believe everything the calculator tells you and think that that's how it works. And so you got to be really careful. Plus, we don't ever talk about the R and R square values in AP pre-calculus. So I think it's good that we not avoid them, but we don't bring up that can of worms until students are ready for it in an AP stats class.
One thing we do talk about in AP pre-calculus, I'm sorry, Curtis, I don't know the answer to this one either. Does the TI-84 store the residuals somewhere?
Yep, does
Yeah.
the same thing. So the same thing is true about those residuals though too. So they're based upon that
The linear
linear
transformation.
model. So
the transformation.
So are they
so
in VARs also?
no, they're not in VARs. They're actually
Oh, they're in a
underneath in
list.
the list.
Yeah.
So
they're
if you
in a
press
list.
second
Okay.
in the stat key,
Okay.
Yeah.
every
Right
time
down
you
there,
do a
7.
regression, there's one
Okay.
called list residual.
So hit number 7, but don't hit enter yet. Don't hit enter yet. So given that R squared is 1, somebody who's watching answer this, what are all the residuals going to be?
Well, there's a 15-second delay here, Steve. So if you want them to answer that, they're gonna have we're gonna have to stall for a second
All
until
right,
somebody
sorry.
can
Go
drop that
ahead,
in
Tom.
there.
Go ahead.
It's gonna be 0.
Yeah.
However,
Well, one of the reasons I brought this up is, Vicky, Tom, one of the things in pre-calculus is when students do regression, they are asked to create a residual plot. And they are asked to look at that residual plot to see if there's any evidence that the assumptions have been violated, or another way to think about that is if the model is inappropriate. And so these residuals are all stored in this list. It's then quite easy to create a scatter plot of the residuals on the y-axis and the input x values, well, on the horizontal axis. So that's important to know, that they're there quickly, that you don't have to go in and do another whole calculation in some way based on the regression model.
Yeah.
So that's
I
nice.
agree. Yeah.
Sorry, Tom, I apologize.
Oh, no problem at all. Yeah. No, I think, the scoring guidelines, what I was struck by is, if a student just said, "Oh, I'm just going to try several, I'll try a quadratic regression because it looks like maybe part of a parabola, and then I'll try an exponential. Oh, the R squared's better on the exponential. That's the one." That's not what they're really looking at you to make an argument based on the kind of structure of those outputs. You really got to know, those outputs are going by halves for equally spaced inputs. They're going down by a factor of half each time. And that's really what they're looking for, that structure, and not just a trial and error, which regression gave me the best R squared.
Plus the student's going to waste so much time trying to do the multiple regressions just to figure that out, when it should just be an observation that they quickly see.
Exactly. Good point, Vicky. Yeah. All right, I'll stop the share and turn it back over to you, Steve.
I hate to say this, Curtis, I think we're at the end of our time here.
We are.
I know.
Can we keep going until 10 o'clock? Or
that's a bummer. I wish we could keep going till 10 o'clock. But I know that my family would probably appreciate me not being online and talking about math.
Well, great job.
This late at night. So it was a great session. Thank you very much. As usual, folks, we've got a PD certificate that you guys can email me for. I'll put my email in the chat here, and you guys can reach out to me there, curtis@ti.com. Just send me an email. Let me know that you watched this session, and I will send you a link where you can generate a 1-hour certificate for this session. We will be on, and I told you all I was going to look it up, and then I didn't. But I have the in front of me right here. We will be on again on September 18th. Be looking for that on the YouTube channel, the Texas Instruments YouTube channel. I'll be posting a link to that in the next week or so, where you can sign up and make sure you get reminders. And the same thing will be true. We'll be doing PD certificates, and we're going to talk a whole bunch about pre-calculus. So look forward to seeing you in about a month. Thank you very much, and we'll see you soon. Bye, all. All right, we
Very good.
are done.